Well, hi everybody. In this section, we're going to work with scientific notation and how to perform certain operations in scientific notation. Now, you probably remember that scientific notation provides a way to write very, very large or very, very small numbers without using a whole bunch of zeros. And I got a graphic on the screen here that really demonstrates that. You can start out with a $100 bill. It's just a piece of paper, right? Now, if you have 100 of those, you have $10,000, which is a pretty nice stack of cash to have access to. And surprisingly, $1 million is not that big of a pile of money. It's about the size of a suitcase full of $100 bills. Then things start climbing fast. If you have $100 million, well, that would be like 100 suitcases of $100 bills. That's a big pallet full of money. Now keep in mind that $1 million is a 1 with 6 zeros. 100 million, well, that's a 100 with 6 zeros. And then we get to a billion. That's 1 with 9 zeros after it. That's 10 pallets of money. That's a big stack of money. And finally, $1 trillion. But $1 trillion, that's 10,000 pallets full of $100 bills. That's an incredibly large amount of money. And that's actually how much the United States is borrowing against our budget every year. So that's a little bit discouraging. But anyway, we're going to jump in now and work with numbers in scientific notation. I'm hoping the first part of this lesson is reviews from some math and science classes you've had before. And then we're going to look at how to perform the operations of multiplication and division in scientific notation. That will probably be a new concept. So let's take a look. Okay, so let's start by talking about powers of 10. It'll come to no surprise to you that exponent, when applied to a power of 10, means we're going to multiply 10 by itself repeatedly. And the thing that I want you to note there is that if you have a positive power of 10, you're going to get a big number. 10 to the third here gives you 1,000. On the other hand, if you have a negative power of 10, as we saw when we were working with properties of exponents, that negative power of 10 means that we're going to have the reciprocal of 10 multiplied by itself repeatedly. So 10 to the negative 2 is like 1/10 times 1/10, or 0.1 times 0.1. That's going to be 1/100th. Negative powers of 10 yield small numbers. So those two facts are what allow us to put numbers in scientific notation. So you might remember that when you write a number in scientific notation, the front number, which we call the coefficient, always has to have a value with an absolute value between 1 and 10. So here's an example of a number written in scientific notation. We have the coefficient, which is in green here, 8.52. It's between 1 and 10. And we're multiplying it by a power of 10. That's 10 to the 6th. However, 85.2 times 10 to the 5th, that's not in scientific notation. That front coefficient is too big. And 0.852 times 10 to the 5th, that front coefficient is too small. Now, we should be able to adjust numbers like that, and we will in just a minute, but they are not in scientific notation. So let's take a minute and take these 6 numbers and write them all in scientific notation. Let's start with 494,200,000. First of all, we need that front number to be between 1 and 10, so our decimal point should be 4.942. And in order to get the decimal place there from where it is at the end of the number, we'd have to move that 1, 2, 3, 4, 5, 6, 7, 8 places. Now the question is that going to be 10 to the positive 8 or 10 to the negative 8? You may have learned some left and right rules about writing numbers in scientific notation. I don't like those. I like to think about this as being a big number, and therefore it has to be a positive power of 10. So 4.942 times 10 to the 8, and we're done. 0.00992. Well, if we want our coefficient to be between 1 and 10, it's going to be 9.92. And we'd have to move the decimal 3 places to get it to that location. So should this be 10 to the third or 10 to the negative third? Well, this is a small number. It's less than 1, so that should be a negative third exponent. That takes care of that. You might notice that there's a little space between these two nines. With large numbers, we use commas every third place to make the number easier to look at. And with really small numbers, you'll often see an extra space between the digits to make the number easier to look at. 59,000, well, that would be 5.9. times 10 to the, we'd have to move it 4 places to get it from the end of the number to where we want it. And this is a large number, so 10 to the 4th. What about 8.62? Well, 8.620, that number's already between 1 and 10, and so we could say that that is 8.620. And how many places did we have to move it? Well, we had to move it none, so that number doesn't need to be in scientific notation, but if we do put it in scientific notation, it's going to have an exponent of 0 on it. Okay, these last two numbers are numbers that are in sort of scientific notation. They have a coefficient and a power of 10, but the coefficient is not between 1 and 10 where it should be. So be careful with these. First of all, our coefficient here can't be 0.000880. That's way too small. We have to make this 8.80. Now, all of the number's value is either located in the coefficient or the power of 10, and we can move that number's value back and forth. It's kind of like a seesaw. If one side of the number goes up, then the other side of the number has to go down. Since we're making the coefficient 1, 2, 3, 4 places bigger than it was, we're going to get that value by taking it out of our power of 10. This has to go 4 places smaller than it was, so the 7 is going to drop down to a 3. 8.80 times 10 to the third. Our coefficient had to get bigger, so our power of 10 had to get smaller. And our last one, 610.0 times 10 to the negative fourth. That coefficient is too big. We need to make it smaller. We're going to make that 6.100. And since we're making the front number smaller, we should make the power of 10 bigger. Now be careful, we're at negative 4. The front number got 2 places smaller. What's 2 places bigger than 10 to the negative 4? It's tempting to say negative 6, but bigger from negative 4 would make us climb up to a negative 2. And we've put all those numbers in scientific notation. The key here is larger numeric values are always expressed using positive powers of 10, and small values are expressed using negative powers of 10. As long as you remember that, then you don't really need to remember any left or right rules for numbers in scientific notation. And that's also going to be useful for when we work with metric prefixes some more in our next lesson. So let's do the opposite. Let's take these numbers that are in scientific notation and put them into floating point notation. So our first one, 5.90 times 10 to the 7th, that's a big number. We're not going to put 7 zeros after that 9. We're going to move that decimal place 7 places to make this number bigger. So we can go 1 place to the right of the 9 and then another to the right of 0, and we're going to have to put 5 more zeros on the back of that. So that's how many zeros we'll need if we move that decimal place 7 places to the right. And then we'll make sure to put in our commas in the right spot. And we end up with 59 million. 9.004 times 10 to the negative 8th, that's a real small number since we have a negative power of 10. Again, we're not going to put 8 zeros in front. 1 decimal place to the left gets us in front of the 9. We're going to need 7 more zeros after the decimal point. So 0 point. And let's leave those spaces to make this number a little bit easier to read. 1, 2, 3, 4, 5, 6. There's our 7th one, 9, 0, 0, 4. We moved that decimal 8 places to the left. This is a small number. We've got this in floating point notation. I want you to pause the video and do the last 3. Write each of those in decimal or floating point notation and unpause when you're ready to see what those look like. Okay, our first one, 1.56 times 10 to the 0. 0 places, 0 exponent means we have to move that decimal 0 places. That is 1.560. Now you might say, well, that 0 need to stay on there? Yeah, it does. That 0 is a significant digit, and so it should stay. We'll talk more about that in just a minute. 2.4 times 10 to the negative 1. Well, this is a small number, so we better move the decimal to make this a smaller number. 0.24. 1 place smaller is 0.24. 8.100 times 10 to the 5th power. 5 places It's going to be a big number. We can go 3 places to the right, and then we'll have to put 2 more zeros on that. 810000. Now, these 2 digits were sigdigs in our coefficient. Those zeros were there to show precision, and so we should put a line over that second 0 to show that those 2 zeros are still showing precision. By doing that, our original number had 4 significant digits in it, and our floating point number also has 4 significant digits in it. So to build on that a little bit more, any significant digits in a number are always contained in the coefficient. The power of 10, those are always going to be your insignificant or non-significant zeros. Only the coefficient contains significant digits when a number is written in scientific notation. It's generally true that the typical adult has about 1.10 times 10 to the 5th hairs on their head. How many sigdigs are there? Power of 10 doesn't matter. What matters is that there are 1, 2, 3 significant digits here, 3 sigdigs in that number. That 0 is significant because it's showing precision. Now, as a little exercise here, the average person's hair grows about 6 inches per year. So if they have this many hairs and every hair grows 6 inches per year, let's figure out how many total feet of hair somebody's scalp can produce each year. To do that, we're just going to take 1.10 times 10 to the 5th, that's how many hairs on a typical scalp, and we're going to multiply that by 6 inches. Now that 6 can be multiplied by our coefficient to become 6.60 times 10 to the 5th. If we put that into floating point form, that's going to be 660, and we'll need 3 more zeros on that. So 660,000 inches. Now let's convert that into feet. We'll put that over 1 and use our conversion fact that 12 inches is equal to 1 foot. That'll cancel off our inches. And if you perform that division, 660,000 divided by 12, you end up with 55,000 feet. Now you might be curious, how many miles is that? Let's go one step further. 55,000 feet. You could look on your conversion sheet to verify that there are 5,280 feet per mile. And so if we take 55,000 and divide it by 5,280, we get 10.4. Notice that we had 3 significant digits on our original measurement, but we only had 1 sigdig here when we multiplied by 6. So that really limits us. Our answer can only contain 1 significant digit then, so we can't call this 10.4 miles. We can really only call it about 10 miles of hair, because we're not really measuring how much hair each person grows that accurately with lots of sigdigs, so we can't claim more than that here. And in fact, 55,000 feet, by that same logic, we would have to round that up and call it about 60,000 feet with 1 sigdig. So that's pretty surprising that if you were to combine all the hair growth potential of your head produces about 10 miles of hair per year. Okay, let's move on and work with the operations in scientific notation, adding, subtracting, multiplying, and dividing. When we go to add and subtract, we can add and subtract numbers in scientific notation very easily if they have the same power of 10. If they don't have the same power of 10, then they need to be changed so that they do before we can add or subtract. Let's take a look at some examples here. Our first one, 4.89 times 10 to the negative 6 minus 1.35 times 10 to the negative 6. Notice here that the power of 10 is the same. That's good news. That means all we need to do is take 4.89 and subtract 1.35. We can just apply that operation to the coefficients. If we take 4.89 minus 1.35, we get 3.54. And since those are both powers of 10, it's like adding like terms in algebra. These are like terms. We would say that those are 10 to the negative 6th. And we're done. Our next one, 9.66 times 10 to the 4th plus 7.32 times 10 to the 4th. Here again, our powers of 10 match. That's good news. All we need to do is take 9.66 plus 7.32. And if we add those two things together, we get 16.98. And then our power of 10 is 10 to the fourth, so times 10 to the fourth. Okay? There. But the problem is the 16.98 gave us a coefficient that's too big. Anytime we perform an operation in scientific notation, our results should be in scientific notation. So we need to adjust that. If we make this coefficient, which is too big, 1 decimal place smaller, will be in good shape. We should call that 1.698. And since the coefficient got 1 place smaller, our power of 10 can go ahead and get 1 place bigger. Those are now 10 to the 5th power. And we've got this in scientific notation. Okay, our third one here, 4.05 times 10 to the 7th plus 3.32 times 10 to the 6th. Those powers of 10 do not match. We need to make one of them match the other. It doesn't really matter which one we change, but in general it's a better practice to make anything that's too small bigger. So we're going to make everything match the larger power of 10. We're going to leave that 10 to the 7th then, and we're going to rewrite 3.32 10 to the 6th using 10 to the 7th. So if I make the 10 to the 6th into 10 to the 7th, that is to say if the power of 10 has to go one spot bigger, then our coefficient has to go one spot smaller. That becomes 0.332. And now that the powers of 10 match, we can add our coefficients. 4.05 plus 0.332, our new coefficient, and that becomes 4.382. And those are now 10 to the 7th. Our coefficient is between 1 and 10, which is what we like. We're done. Okay, let's do one more together. 7.54 times 10 to the negative 13th plus 6.906 times 10 to the negative 11th. Those powers of 10 do not match. We can either make them match the negative 11, the negative 13, or we could split the difference and go to the negative 12. But again, the best bet is to go to the larger power of 10. Now be careful here. It's tempting to say the negative 13 is the larger, but it's not. Negative 11 is bigger than negative 13. And so we're going to change both of these to 10 to the negative 11th. So if we change this number so that it becomes 10 to the negative 11th power, it's going up by 2 places. That means this has to go down by 2 places, and our new coefficient is 0.0754 times 10 to the negative 11th. And now that our powers of 10 match, we can combine those coefficients. 0.0754 plus 6.906, that becomes 6.9814. And those are now 10 to the negative 11ths. Okay, I'd like you to do the last one. Take a minute and subtract 9.55 times 10 to the negative 8 minus 5.05 times 10 to the negative 7. Go ahead and do that one and unpause to see how that works out. Okay, the powers of 10 do not match, and we want to go to the bigger power of 10. Negative 7 is the bigger power, so that means we need to change 10 to the negative 8 to become 10 to the negative 7. Since that's going up one spot, this has to go down one spot. That means it's 0.955 times 10 to the negative 7th. Now our powers of 10 match, and we can subtract. We have 0.955 minus 5.05. That leaves us with negative 4.095, and those are now 10 to the negative 7ths. It should make sense that we get a negative number here because 9.55 times 10 to the negative 8th, that's a smaller number than 5.05 times 10 to the negative 7th. So we're taking a smaller number minus a little bigger number. Yeah, it makes sense that we get a negative value. If you got that, nice job. If not, you might want to rewatch that and make sure that you see where you made your mistake. Okay, now you might be saying, well, why do we have to do that? I could do that on my calculator. You're right, you can do that on your calculator, and you should be able to verify your work on your calculator. But we're doing it using those powers of 10 so that you can see how the numbers behave and get a better sense for how those powers of 10 interact. Now, if you take a look at your calculator, let's just do that same problem that we had on the last screen, the one that you did for practice. Let's just do that directly on your calculator. You should have one of three buttons on your calculator, depending on what brand. You might have an EE button, an EXP button, or a times 10 to the X button. Okay. A common mistake is for somebody to enter in a times 10 when they're doing this, but you don't need to do that. So to do the problem that you can see on your screen here, you're simply going to enter 9.55. My calculator has the EXP button, and it shows on the screen that's times 10 to the -8th. And I'm going to subtract 5.05. There's my EXP button again. Notice we don't have to hit times 10. That'll put you a decimal place off. Don't do that. That's a common error. Times 10 to the -7. Well, your calculator puts that into floating point form. Now, some calculators will have a button where you can just automatically change that into scientific notation, like this calculator does. It's got an SCI button that'll automatically change that to scientific. But some calculators you actually have to change the mode. And again, I won't try and do that for every calculator, but if you have trouble, I'll show you. On this calculator, we're going to go into Setup. That's for floating point, scientific, we know what both of those are, or engineering notation. We're going to see that in our next lesson. And we're going to choose 0 to get into that menu. And now we'll hit 1 to say that we want it to report answers in scientific notation. And there it is. It took our previous answer, 4.095 times 10 to the -7th. That's what we had just a minute ago. So just to emphasize, you can double check your work on your calculator today, but we're trying to figure out what these results are by handling the power of 10 on our own and not relying on the calculator to do that. I trust you can figure out your calculator. If not, let me know. Okay, multiplication. When powers of 10 are multiplied together, we just add their exponents. We saw that when we were working with properties of exponents in a previous lesson. 10 to the 3rd times 10 to the 4th is 10 to the 7th. The thing to notice here is that the powers of 10 do not need to match. So let's take a look at just a couple examples here. Okay, our first one, 4.7 times 10 to the 3rd times 1.3 times 10 to the 9th. Well, we can just multiply those coefficients together. Again, the powers of 10 don't have to match to multiply, and we get 6.11. And 10 to the 3rd times 10 to the 9th, these are all just being multiplied together. Add those exponents, that gives us 10 to the 12th. We're in scientific notation. Done. That's all there is to it. What about the next one? 6.5 times 10 to the -8th times 2.8 times 10 to the -12th. Well, the powers of 10 don't need to match, but we can multiply these two together and get our new coefficient, and that turns out to be 18.2. Now we'll multiply our powers of 10 together by adding the exponents. -8 and -12 gives us -20. Okay. However, our coefficient ended up being too big there, so we need to make an adjustment. We're going to call that 1.82. And since our coefficient is going to get one spot smaller to be where we want it, our power of 10 has to go one spot bigger, and bigger than -20 is -19. There's our result in scientific notation. Now our last one we want to explore a little bit. We want to take 7.50 and square that. One way to do that is, of course, to just write that out as 7.50 times 10 to the -3rd times itself, because then we can multiply our coefficients together and get 56.25. And we can multiply our powers of 10 together and get 10 to the -6th. But our coefficient is too big there, so we're going to have to adjust that and make it 5.625 times 10 to the, since this is getting smaller, that needs to get bigger, and that climbs up to a -5. There, and we're done. But the other approach that you could take on that would be to use our properties of exponents. One of our properties of exponents said that if two things are multiplied together and there's an exponent on both, we can apply that exponent individually. So that means that we could rewrite this as 7.50 squared times 10 to the -3rd squared. Now we know that 7.50 squared is 56.25. And when we have a power to a power like we have here, 10 to the -3rd squared, we multiply those exponents and we get 10 to the -6th. Now, of course, that has to undergo the exact same adjustment we did a minute ago, and again we would get 5.625 times 10 to the negative fifth, and we're done. And that leaves us with just one more task here. We know that when we multiply powers of 10, we add those exponents, and then it makes sense that when we divide powers of 10, we subtract those exponents. We saw that in our previous lesson as well. 10 to the 7th divided by 10 squared is 10 to the 5th. I like to write division as a fraction. If we take 9.1 and divide it by 2.6, that gives us a new coefficient of 3.5. And 10 to the 15th divided by 10 to the 6th, we subtract those exponents and we get 10 to the 9th. Our numbers in scientific notation, that's all there is to that. Now, the thing that can happen though that we haven't really acknowledged is we can end up with some significant digit problems. In our next one, 1.72 times 10 to the negative 7th. 1.72 times 10 to the negative 7th is going to be divided by 5.03 times 10 to the 1st. Well, when we divide those coefficients, we get a whole screen full of digits here. We get 0.341948. That's way more sig digs. So we just follow our rules for sig digs. We're dividing 3 sig digs by 3 sig digs. We better keep 3 sig digs. 0.342. So you never have to ask where to round. The sig digs tell you where to round. 10 to the negative 7th divided by 10 to the 1st. Subtract those exponents. That's going to be 10 to the negative 8. Now our coefficient's a little bit too small here. We better make that a little bigger and call it 3.42 so that we're between 1 and 10. And if we're having to make our coefficient bigger, our exponent's going to have to get smaller. That's going to drop down to 10 to the negative 9th, and we're done. Okay, I want you to do that last division. Do 6.571 times 10 to the negative 3rd divided by 4.113 times 10 to the negative 4th. Unpause when you're ready to see that solution. Okay, when you divide 6.571 by 4.113, you should get a screen full of digits, but we only have 4 sig digs in each case, so we can only keep 4 sig digs. We're going to call that 1.598. And our power of 10 is going to be 10 to the negative 3rd divided by 10 to the negative 4th. Be real careful here. Tempting to say negative 7, but in fact, if we take that exponent of negative 3 and subtract the bottom exponent of negative 4, we end up adding that 4 on. Negative 3 minus a negative 4 becomes negative 3 plus 4, which turns out to be 1. So watch out for that, and hopefully you didn't make that mistake. That's an easy mistake to make. That number is in scientific notation and we're done. However, it's just barely bigger than 1.598, so we could also just put that in floating point and call it 15.98, and then we're done. Okay, one last problem here to tie in the work that we've done with order of operations. 8.10 times 10 to the 3rd squared minus 5.30 times 10 to the 6th. Pause the video, see if you can work that out, and unpause when you're ready to see the solution. If you can do this problem, then you can do just about anything. This is our last problem, and then we're going to bring this to a close. All right, here we go. 8.10 times 10 to the 3rd squared. Let's do that first. Order of operations says we should do this exponent before we do that subtraction. So the 8.1 is going to be squared, and the 10 to the 3rd is going to be squared. 8.1 squared gives us 65.61. And 10 to the 3rd squared. Tempting to say 9 there, but multiply your exponents. That's 10 to the 6th. And from that, we're going to subtract the 5.30 times 10 to the 6th. Now, usually we don't like it when our coefficient is too big like it is here, but since our powers of 10 match and we need that to be the case, we're just going to leave it alone. 65.61 minus 5.30, that turns out to be 60.31, and those are now 10 to the 6ths. However, that coefficient is still too big. Let's make the adjustment and call that 6.031. And since this is getting smaller, our power of 10 must get bigger by one spot. 6.031 times 10 to the 7th. And if you can do that, you're in good shape. Okay, well, I think that wraps up everything that we wanted to do. You know how to put numbers into scientific notation, take them out of scientific notation, and perform all the common operations both by hand and using your calculator. Now, I did want to point out that if you use your cell phone calculator, it's not unusual to not have a power of 10 button, and then you'll just type in the times 10 manually, which is exactly what you should not do when you're using your calculator. So using your cell phone calculator, which has its limitations, you're going to have to type in the times 10. Okay, well, be sure to let me know if you have any questions about your calculator use or anything else, and I'll help you out. Otherwise, we'll see you in the next lesson where we're going to build on this idea and establish what engineering notation is. So we'll see you there.